This is a great opportunity for us all to get together and talk about remote sensing of ET, and I really look forward to being a part of this conference. What I'd like to talk about today is a project that we've been working on in California using a combination of remote sensing via energy balance and vegetation index-based approaches with root zone water balance modeling to improve estimates of groundwater extraction for the Kaweah Delta Water Conservation District. I'd like to acknowledge my co-authors, my colleagues, Lindsay Hall with David's Engineering and Larry Dotson with the Kaweah Delta Water Conservation District. We feel that this approach is a good opportunity to leverage off of available energy balance data sets, base data sets of ET, to improve pumping estimates over a wider time frame. In this case, we had essentially 1 year's worth of seaball data on actual ET, and we're able to extrapolate that over a 12-year period using NDVI and the root zone water balance to, we feel, refine estimates of actual ET in the area of interest. I'll just provide a brief background on the Kaweah Delta. Then I'll talk about the approach that we've used, and then provide a comparison of the results of the root zone water balance back to seaball results, both for the year in which we had the seaball data and then for 2 additional years where data was available but wasn't used to calibrate the model. The Kaweah River Delta is located in the San Joaquin Valley of California, about halfway between Fresno and Bakersfield. The dotted black line on the graph shows the overall watershed in Kaweah Delta area. The red line is the Kaweah groundwater subbasin, and then the green hashed area is the Kaweah Delta Water Conservation District. The district contains a couple of urban areas, Visalia and Tulare. The district was formed in 1927 to develop and preserve local water supplies, both surface and groundwater. As part of their groundwater management role, the district is a designated monitoring entity for the state, so they report to the state annually as part of what's called the CASGIM program on groundwater levels in the subbasin and groundwater quality. As part of implementation of their groundwater management plan, which they adopted in 1995, they report annually, develop reports annually on groundwater conditions in the basin. They've developed a numeric groundwater model as part of their management efforts. And the focus of this talk is really on their estimation of annual groundwater pumping within hydrologic units within their service area. This map just shows the blue dots represent direct recharge basins. The red areas represent planned recharge basins. So they have an active program of both direct groundwater recharge and in lieu recharge through the importation of water supplies via the Kaweah River and from the Central Valley Project. The service area consists of 6 hydrologic units shown here in black, for which they report groundwater pumping. The gross area is 340,000 acres, of which 285,000 acres are cropped. The data here is from a combination of land use surveys from the Department of Water Resources of California for 2003 for hydrologic unit 6, which is in Kings County, and 2007 for hydrologic units 1 through 5, which are in Tulare County. And those surveys provide field-level identification of crop types and irrigation methods and are completed on about a 10-year interval, 5 to 10-year interval, typically. The major crops are dairy support crops, field and truck crops like cotton, winter grain, and corn in rotation are shown in yellow. Pasture and alfalfa are shown in green. Deciduous orchards are shown in brown, and vineyards are shown in purple. Also, there's some citrus up along the Sierra foothills there. Now, the subbasin has experienced overdraft over time. This graph shows in the light blue bars their percent water year in terms of their surface water supplies. The blue line shows their fall annual groundwater elevations averaged across the area. And then the red line is just a trend line. One of the things that I guess the 2 main factors contributing to the depletion are that surface water supplies are not adequate to meet demands. And also the agricultural area has increased in time as well as the urban area. So there's an increasing demand on water. Previous estimates of agricultural groundwater pumping have been based on ET calculated from published crop coefficients, empirical estimates of effective precipitation using the NRCS National Engineering Handbook methodology, and an assumed consumptive use fraction, often referred to as irrigation efficiency, which is the ratio of the ET derived from applied water to the applied water amount. And then these 2 equations just illustrate how, in a simple sense, how These inputs are used to estimate total applied water. We have the ET minus the effective precipitation, which is the ET derived from applied water divided by the consumptive use fraction. And then the groundwater demand is estimated based on the total applied water minus the surface water deliveries available in any given year. And these calculations are done at the hydrologic unit scale. There are causes of uncertainty in this estimation method. Cropping data is not available frequently, so to the extent that there are changes in cropping patterns within hydrologic units from year to year, we're not able to capture that. There can be double and triple cropping, and those cropping practices can change from year to year depending on market forces, for example, crop prices. I would imagine there's a greater intensity in cropping this year, for example, with the feed prices going up and the dairies in this area. Also, there can be differences between idealized and actual growing conditions for the multitude of reasons that Rick mentioned earlier in his presentation. Additionally, it's difficult to estimate the consumptive use fraction because there's not a lot of a lot of information to describe on-farm irrigation practices. So that led us to this approach of combining remote sensing with root zone modeling, where we developed a relationship between the normalized difference vegetation index and a basal crop coefficient from available actual ET data from CBOL for 2007. And then we parameterized and applied a field scale root zone water balance model for the 1999 to 2010 period to estimate various fluxes. Total ET, ET of applied water, total applied water, deep percolation of precipitation and applied water, and other flow paths. Benefits of using this approach is that there's a limited dependence on cropping data. We're using the NDVI signature to help us estimate transpiration. So to the extent that cropping patterns or practices change from year to year, we're better able to capture that, inherently accounting for double and triple cropping. And by developing this relationship based on actual ET, to the extent that the stress conditions or whatever else is causing a departure from potential ET to actual ET, to the extent that that's stable over time, this relationship should be applicable over time. Another benefit of this is it's less costly than applying an energy balance approach each year. I should note that one area of improvement that we don't have here is any improved understanding of on-farm irrigation practices. So there's still significant uncertainty in the groundwater pumping estimates because we don't know exactly what that consumptive use fraction is. So the relationship we used was based on the work of Iraqi et al., where we estimate a maximum transpiration coefficient, which occurs at a certain maximum NDVI value. And then we estimate a minimum NDVI value at which we expect no transpiration to occur. And so those were estimated from the 2007 CBOL analysis for the district. And then we adjusted those for individual crop irrigation method groups as part of calibrating the root zone water model so that by crop and method group, we were able to get the total ET to agree with CBOL, which we're regarding as the standard in this case. So here's a look at how we developed the relationship. We basically created a scatter plot of the actual crop coefficient from CBOL versus the NDVI values for 8 image dates for individual fields. And that's kind of the black cloud you see there. The areas of relatively high crop coefficients at low NDVI represent evaporation, and sort of the base of this curve represents what we think is the basal crop coefficient. So in order to get this relationship, we estimate an NDVI minimum value at which we expect transpiration to be 0, a maximum NDVI value which we expect to see in any given image. And we set that a little bit higher than what we saw in 2007, just allowing for variation over this 12-year period. And then estimate a maximum basal crop coefficient at that point. This was done for the top 10 crops. Those are listed there. Corn, which is typically preceded by a winter grain crop, even though it's not identified by the crop survey, is the primary crop, followed by alfalfa, walnuts, cotton, pistachio, field crops, vineyards, plums, oranges, and then fields that are actually identified as being double cropped. So the field scale NDVI analysis consisted of processing 154 images over the 12-year period. We included 13 MODIS images to help us where we didn't have available Landsat imagery or where we had significant cloud gaps within the service area. Our rationale for selection was to minimize those cloud gaps, to provide coverage throughout the year, and to increase the frequency of imagery processing during the peak growing season when most of the ET is occurring. In terms of NDVI processing, we extracted the average NDVI for each image date by field, and then applied linear interpolation to develop a daily time series over the 12-year period. So here's just an example of one field that was generally classified as a field crop field from 2002 through 2010. And we can see quite a bit of, we don't know the specific crop types necessarily from year to year, but we do see quite a bit of difference in the NDVI signature from year to year depending on what they're doing out there. For example, in 2009, we can see that it appears that they had a winter grain crop followed by probably corn. The field scale daily root zone water balance is based on the FAO 56 dual crop coefficient approach, where we estimate daily total evapotranspiration based on reference ET from the California Irrigation Management Information System. And then we multiply that by a crop coefficient that combines an evaporation coefficient estimated based on a two-stage evaporation model and our basal crop coefficient from this NDVI relationship. And I include KS here because just to emphasize that the basal crop coefficient relationship we're developing accounts for stress to the extent that seaball can account for actual ET as opposed to potential ET. Through the model, we simulate individual irrigation events to estimate the evaporation component of ET and to estimate the total applied water over time. On the right, we just have a schematic of those flow paths for the root zone water balance. We neglect horizontal subsurface inflows and outflows because we don't feel those are significant. So here's just a couple of graphs showing the root zone model results for a double cropped field that is probably winter grain followed by corn. The solid black line in the top group is the basal crop coefficient. The dotted line shows the impacts of evaporation due to irrigation or precipitation. In the bottom graph, we have the actual magnitudes of calculated or estimated daily evaporation over this year. The black line again shows the transpiration component. The dotted line adds in the evaporation component. The red spikes indicate simulated irrigation events, and the green dots along the bottom are precipitation events. We didn't have a lot of precipitation in 2009. So to calibrate the model and to compare it to available data sets, we developed this NDVI relationship, as we discussed previously, based on one half of the fields using the 2007 Seaball ET. And then we iteratively, comparing the results of the model back to the Seaball results, we iteratively adjusted the KCB max parameter for general crop irrigation method groups. And that allowed us to correct for any potential differences in that actual basal crop coefficient versus NDVI relationship that might exist among crops, as well as any biases in our evaporation estimates from the root zone water balance model. Then we took the remaining fields and compared those to the Seaball ET from 3 data sets that were available: 2007, 2008, and 2009. In 2007, we had 14 images spanning the period from January to December. 2008, we had 14 images spanning the period from February to November. In 2009, we had 8 images spanning the period from April to October. And so what we have here is a series by year of scatter plots showing the total ET for each field as calculated for using Seaball on the x-axis and using this root zone water balance model on the y-axis. So overall, the results fall close to one line. When we look at the area-weighted average depth over each year, the differences are within 1%. But differences for individual fields can be quite large. On average, they were about 108 millimeters, or 13% of the total ET for the field. Then we looked at a comparison of model results to Seaball by hydrologic unit. And here we see bigger differences because we're kind of disaggregating the data. And that's something we like to look at refining. In all cases over the 3 years, the differences were within 10%. Over the 3-year periods, they tended to be within about 5% on average. So future work, additional refinement of the root zone model parameters and procedures. A lot of that I think we'll be looking at how we're estimating evaporation and the specific parameters we're using there. An uncertainty analysis of actual ET and applied water using this approach. So we can estimate the uncertainty in the individual inputs and then estimate the overall uncertainty in the results. And then an evaluation of the differences in the results from what's been done previously, just to verify whether this is really making a difference in terms of producing different results. regardless, we think it's increasing the certainty of the results. So with that, I'll just ask if dust abatement for ditch banks via wave runner is a beneficial use of water.